Show operate. How do you guys log in so fast after I log in? Are you sort of logged in and then it puts you in automatically as soon as I start the meeting?
Yeah, we're like waiting for you, and then it just puts us in automatically.
Okay, cool. But it's fast, but it's not instant. I mean, it's like they're 1 second apart as you come in. And that's slow by computer standards.
Honestly, I think I just got lucky.
Oh.
I think I logged in at the exact same time as you started.
Well, I mean, we have a nominal starting time, and so you know, it's not like looking at the wall clock and deciding to make it to your 2 o'clock class. We're all stuck sitting at our computers, and there's a clock right on the computer, which they're all synchronized now down to the second. So I guess we'll all begin at the same time. Is it working? Yes, that's my wife photobombing us there. So. Is it working? Yeah, there you are. Okay. It's called Zoom bombing, but that's something else. Oh, yeah, whatever. Okay. All right. Hey, before we get too far into this, we have a couple of things to figure out here. First of all, we have a test coming up. I'd like to have another test soon. And I'm just not really sure how to do this. So we decided the test would be on the 17th, right? A week from today. Does anybody remember that? That was my memory. Okay, how shall I give you a test and how shall you give it back to me? If I simply put a link to it on Canvas or something, make a PDF file that you guys can download, is that going to be sufficient for you guys? I mean, it would just be a handful of questions for me to give to you. And then have you guys all succeeded in turning in papers? Do you know how to turn in the papers on Canvas? Is that working? I have to think of how I do that again. I don't remember. But if I give you guys a spot on Canvas to turn in your paper, are you all going to be able to scan your work somehow? I'm not expecting you to type anything up, but just to, unless you feel like it, but just to write out your answers and scan them. All right. For my calculus students, we are considering doing like a multiple choice question. Not multiple choice. Yeah, multiple choice. I can do that for you guys for some like computational questions, but this is a proof-based course, and I've been giving you guys more and more proofs as we go on the homeworks. And I would like the tests to be a lot of proofs as well. So kind of not wild about multiple choice, but do you want multiple choice or something? No. I'm trying to make this, how shall I put this? The dean and the provost are regularly reminding the faculty that we need to be accommodative, because obviously you guys you've had your college career has just been messed up by some pandemic. And not everyone has the facility to do a lot of technological things. Not everyone has the freedom in their schedule to do things at the moment that I tell you to do them. And so we're working around that. And I'm trying to be accommodating to you guys if you have an idea for how you'd like the test to go. So if I don't hear anything from you guys, I guess what I'll end up doing is writing a test that kind of feels like the one you had last time, except I will probably give you like 24 hours to do it. I'll post it at a certain moment, and then you guys have to turn it in by 24 hours later. If you have suggestions for what you want on the test, or you want more computation or less computation, more proofs, less proofs, drop me a line. Would you just send me some email, or if you want to say something now, because I do have a few days before I have to actually figure out what to put on the test. So now's the time to make your wishes known.
Personally, I liked last test. Like I kind of like running through the algorithms and doing the computation and just a little bit of proofs here and there.
All right. I can't let you go with no proofs because that is one of the features of this course is that we're supposed to get students more, more into the groove of proofs. So sorry, there's proofs in there. I guess we actually have have to go through my notes here. So in terms of what computational problems we have had, I don't quite remember where we left off on the last test, but sometime by the time of the last test, we were working on the Chinese remainder theorem, finding inverses, modulo composite numbers, and so on. And now we've been using that kind of idea to do things like computations of powers modulo n, especially using the Fermat and Euler theorems. We've had Wilson's theorem that would enable a lot of fast calculations, that kind of thing. Are there any other algorithmic kinds of things that I've taught? Oh, we did talk about the encryption game last time. So that's a very specific process that involves multiple ones of those steps that I just mentioned. You are computing powers modulo n, but in order to do the decryption, you also have to be able to find an inverse modulo phi of n, that kind of thing. So let's put it this way. If there are algorithmic kinds of questions that you would like on the test, tell me, and I'll try to put them on. And the same thing with if there are theorems or ideas that we've had, the more conceptual things, if you want them to be as part of the proofs, I can put them on the test if you let me know what kinds of stuff you'd like to confront. While I'm at it, let me also make the observation that we've now been doing this for 2 weeks on the Zoom meetings. I don't know how it's going. Honestly, when we were together in a classroom, I could read your faces better. And most of you have your video muted, so I can't even see if you're looking bored or looking confused or anything. And that's fine, but that means that it has kind of turned into just me giving you a video lecture, which is entirely appropriate. I know some of you are only looking at this on the YouTube afterwards. But if that would actually be preferable for people, I mean, I could just pre-record the lecture, and if I did that in advance, I suppose I could have better looking slides and edit things and so on. So that would be a plus, but the minus then is that there would be no chance for interaction. So do we need to change course a little bit? We're still going to be going this way for another month. So if these Zoom classes aren't working for you, maybe you better tell me. Is there anything that you want to suggest as a change, new ideas or anything?
Personally, I'm fine with either way, but I feel a little more comfortable when we're all together because, I don't know, it sort of gives me the discipline to actually pay attention.
Yes. Yeah, I mean, this comment has been made. So again, the faculty are talking amongst themselves here, and one of the things that we do know is if it's a pre-recorded lecture, you have to make it be a lot of smaller lectures instead of one long one, because nobody could just sit and watch. I couldn't even watch The Mandalorian last night. My stepson wanted to watch this, and I'm like, after 20 minutes, I'm just falling asleep. And that's with gunfights, and I don't know what else is going on in there. So by comparison, I know sitting for an hour of number theory would be a little boring if you can't at least feel like there's somebody that can answer your question if you get confused. So it would have to be different if I pre-recorded it. Well, I like it if it's live. I wish we were together. Honestly, I wish I could see you guys face to face. I'm enjoying the office hours. Some of you have been showing up for office hours, and that's great because then I have a one-on-one or a n-on-1 where n is between 1 and 30. Again, let me just say, you can always send me an email with a suggestion or a comment, and I'll try to take it into account for the rest of the class. But until I hear something different, I'm going to kind of keep plowing ahead the way we've been doing it, and see if we can get as much number theory in there as people want. All right, so
Can I ask a question about the exam?
Oh yeah, go
If
ahead.
it turns out to be like 24 hours long, then how much time do you think we will actually need to solve the exam?
So I'm making it 24 hours because people like you especially, I know, are in a completely different time zone. So I want people to feel comfortable working on it at their own appropriate hour. I know myself, I know that once I realize you have more than an hour to take the exam, it'll stretch into a longer exam. But I don't want to make more questions than last time. I thought it was plenty long last time. So probably if you can give yourselves a 2-hour block of time, that should be enough, I would hope. Please make sure that you leave a little extra time just to get the thing scanned and uploaded and whatever. And if I can make a suggestion, don't wait until the last minute, because you never know. Just when you're ready to file your paper, that's when the internet's going to go down in your neighborhood. And we've all had that happen, right? So try not to procrastinate on the test.
Okay, thank you.
I thought actually when you started your sentence, I thought you were going to ask a question on the homework, because I've gotten a lot of people asking me questions on the homework.
Me?
Well, you said, can I ask you a question about? Then you said the exam, but I was anticipating the rest of your sentence before you got there, and I thought it was going to be about the homework. So I'll tell you guys, I asked you to do some calculations invoking Euler's theorem and the principles behind that, and some of that fast power, but use the squaring method to calculate powers fast. And I do have to apologize, because when I ran the numbers before I assigned them to you, I thought that the powers of 3 modulo 2047 started to repeat pretty fast, and it turns out they don't. So nothing in the homework set that I assigned for you is wrong, but those of you who tried to actually compute 3 to the power of 2048 with 11 successive squarings, you might have noticed that even after you got the swing of how to do the calculations, it probably took you a good 15 minutes or more to carry it out by hand. If you did it with a computer to just, if you instructed the computer how to actually do the stuff fast, and you just use the computer to do the reduction mod n or something like that, that would be fine, and then it could be done kind of quickly. I did search around for some other combinations of a modulus n and a base a that would exhibit the repeating pattern that I had thought I had observed. So that's why I adjusted the homework the way I did, but whichever way you're doing it, that's, whichever one of the variations on that problem, I'll take them either way.
Do you have a suggested calculator for that, for doing the modulation? Or you would have been using Maple, I think?
I have, but that's because Maple puts a bunch of things into one. But just, I've spoken to a few of you in office hours, and you've seen me pull out my phone. My phone just has an ordinary calculator, and if I want to reduce the number 176,400 modulo 2047, I just type in first the big number, and then the division symbol, and then the modulus. Before I hit equals, the calculator is already in little faint numbers. It's already telling me what the answer is going to be, so I can spot the integer part of the quotient. So in the statement of the division algorithm, that's the Q. And so then when I touch my phone in the right spot, I can erase the division symbol, and instead I write minus 86 times. And then when I hit the equals button, it's giving me the reduction of 176,400 modulo 2047. It's doing the reduction. It's giving me the R from the division algorithm. So you can do it with a very primitive calculator, and I know you can do it because I could do it. I have used Maple for a long, long time, so I'm used to its syntax. There are other similar products like Mathematica and I think MathCAD and so on. These are
MATLAB also works just fine.
MATLAB, yeah. These are things that are intended as like giant all-purpose mathematical aids. And a lot of my engineering students, for example, have access to these things because they don't want to think about the math at all. They just know they have to do a lot of calculations. Honestly, you could probably rig up a Microsoft Excel spreadsheet to handle this kind of business of computing successive squares or anything that you're doing in an iterative way. I don't know all of the Excel primitives for things like getting the integer part of a fraction so that you can get that number 86 that I was just describing in the previous paragraph. But I'm pretty sure you could just write it up in a spreadsheet, and then it doesn't even have to be Microsoft, of course. I use LibreOffice for my spreadsheet handler, and learning how to use a spreadsheet with little formulas in the boxes. That's something that turns out to be very useful for anybody who has to face the working world at some point in their lives. So much as I dislike Microsoft in general, you can probably make that work. I don't know, is anybody else using some software that they want to recommend? Wolfram Alpha, probably. You could just plug it in. Not sure. I am trying not to make this too computationally intensive a course, but I can propose little projects. A couple of you wrote me, and I'm sorry I didn't respond, projects involving things like primality testing and so on. If you can code up in any language the kinds of routines that we've already been working on, as long as your machine can handle integers that are fairly large, the largest integer that your machine can handle, I will give you examples that are that big, and you can see that the algorithms that I'm describing for you work actually quite rapidly. And they could do things like discover whether a number is prime and find the factors of a number that's known to be composite. I mean, to the extent that our mathematical understanding, the universe's mathematical understanding has progressed, I know of certain algorithms that I can give you, and if you want to try putting them into a machine, that could be fun. I enjoy it on my off days, and you might as well. Good. Any other sort of general comments that you guys want to make? I mean, there's some new material that I want to discuss from chapter 7, but I'll take any other questions or anything. All right, let me swing this around and we'll talk about some math then. All right, so one of the things that we noticed about the Euler phi function was that it had this multiplicative feature, that if you want to calculate phi of a product, that was the product of the two values of phi, and that assumes that you have two numbers m and n which are co-prime. And I actually gave you two proofs of this. One was kind of pedestrian and the other one was a little fancy, and it talked about the integers modulo m, the invertible elements mod m times n. And at the time that I gave you this theorem, I remarked that there's a phrasing for this. We say that the function phi is multiplicative. And that phrase actually gets used because it turns out to happen kind of a lot. This Euler phi function is maybe the most important one, but I did also mention the Möbius function, the one that's only got three values, +1, -1, and 0. That's another example of a multiplicative function. I want to show you a couple of others today that are actually also kind of interesting. And then I'll, if we have time, I want to link that with the theorem that explains how some functions are multiplicative because other functions are multiplicative. So, one of the functions that I'm interested in is, it's usually indicated with a sigma. So that's the function that's defined on, let's say, positive integers. And it's sigma of any positive integer is equal to the sum of all of the divisors of n. So there's a few examples to be aware of. If you take sigma of a prime number, the only divisors of the prime number are 1 and p. And there's another number that's actually got some historical significance, another small number, and that's sigma of 6. That is, the divisors of 6 are 1 and 2 and 3 and 6. Obviously, divisors always come in pairs, right? To say that 2 is a divisor means that 6 can be written as 2 times something. Well, that something would be 3. So in this case, the sum of the divisors is 6 and 6 makes 12. I just said something about pairs, but do keep in mind that there's a limit to that sense. If you take a number that's a perfect square, then yes, the numbers do come in pairs, except for the fact that some numbers have to be paired with themselves. So the number of the divisors is not necessarily even. And I get whatever I get when I add those numbers up. And one more, I guess I'll do the number 12. 12 has a lot of divisors, so since this is not a perfect square, then they will come in pairs. 1 goes with 12, 2 goes with 6, 3 goes with 4, and I guess I'm done. And so the sum of these is, there's 6, 12, 24, that's 28. All right, obviously I could pick any integer, find all the divisors, add them up. You may not see much of a pattern developing. But I will point out that when you have a number like 12 that has a lot of divisors, then when you add those divisors up, of course you're going to get something that turns out to be, well, comparatively big. I mean, every number, when you start to list its divisors, you always have the divisors of 1 and the number that you started with. So the sum of the divisors are always going to be bigger than the divisors, the number that you're looking at in the first place. Well, I guess except sigma of 1 is just 1. But the sum of the divisors can be as low as 1 plus n, and in fact it does hit that low when the number n is prime in the first place. But on the other hand, it can be quite big, quite a bit bigger than the number n that you have in the first place. About 2,000 years ago, people were looking at this issue, and they kind of noticed that, yeah, the numbers seem to come in different types. There were numbers that had a lot of divisors and some numbers that had not too many divisors, and sort of somewhere between not enough and too many should be the numbers that are like just right. It's the story of the 3 little bears. Too few divisors, too many divisors, and just right in the number of divisors. And since the number of divisors seems to be correlated with the sum of the divisors, this kind of became the gold standard for how you decide on whether a number has a lot or few divisors, is to say, look, why don't you just take the number and add up all of its divisors? Because a number like 12 that has a lot of divisors ends up with a very big sum. And by big, I mean that it's more than twice the size of the number you started with. You know you have to have something that's more than the starting number, but does it get to be twice as much? The answer sometimes is yes, and other times no. Sometimes it falls short. So in ancient Greece, the terminology was made that a number is said to be abundant if the sum of its divisors is more than 2n, and n is said to be deficient if the sum of the divisors is less than 2n. And that leaves just one other category, which is the set of numbers for which the sum of the divisors is exactly 2n. And you can see that the number 6 is an example of that. So they had a word for that. They said n is perfect if sigma of n is exactly equal to 2n. So the sum of the divisor function turns out to be a handy way for us to, well, first of all, to define these 3 words. And more generally, it helps us sort of zero in on this idea that some numbers have kind of a lot of divisors and some have not too many. Now you could ask, you know, if you're just interested in the number of divisors, why don't you make a definition for the number of divisors? Very well, I will do that. define a function tau that goes from the natural numbers back to the natural numbers, and it's just defined as tau of n is equal to the number of divisors. That means positive divisors of n. And so for a prime number, you'll have t of n that's equal to 2. That happens if and only if the number n is prime. The only number for which t of n is equal to 1, I know when that happens if and only if n is equal to 1. And the number 12 had a lot of divisors, so if these are kind of the low end of the spectrum, then I don't know, how many divisors did 12 have? 12 had a total of 6 divisors. That looks pretty good, I guess. I don't know. The only reason that I didn't use this in my decision as to how to define the numbers that are abundant or deficient or having a lot or a few of divisors is that I'm not really sure what to compare this to. In the case of adding up the divisors, I guess I know that all of the divisors are less than n, so I guess the thing that I want to compare to it would be n itself. I mean, if you want to put these two things together, you might observe that since every divisor of n is less than or equal to n, you have an easy upper bound on sigma. Sigma of n is the sum of all of the divisors, and if there are this many of them, and every one of them is a divisor of n, then you can't get any bigger than tau of n times n for your sum of all of the divisors. Okay? You got me? Everybody's playing along? You understand these two functions? All right, so I want to come back to the perfect numbers in a second, but let me prove to you the sort of the 20th century, 21st century understanding of these functions. I'll give this to you as a theorem. And the theorem says this. It says that sigma and tau, both of them, are multiplicative functions. So if you had the need to start computing these things, it would be sufficient for you to know how to compute them for prime powers. So in fact, I guess I'd like to take that as a little sidebar. That's a little proposition. If p is prime, and k is any positive integer, then when you want to compute tau of p to the k, that's pretty easy. And sigma of p to the k is only a little bit harder. I mean, it's easier to write it down, but it's you do have to stop and think for a second to get it pretty. Maybe somebody can fill in the blanks for me. What is tau of p to the k?
+1.
Yeah, that's just k plus 1. Because for a power of a prime, the only possible divisors, according to the fundamental theorem of arithmetic, the only possible divisors are the numbers of the form p to the l, where l is less than or equal to 1. So all of the divisors are just p to the l, where l is between 0 and k inclusive, and that's a grand total of k plus 1 entries. And knowing that these are exactly what the divisors of p to the k are, I can add them up by simply writing them all down with a plus sign, but that's kind of a lame way to state the result of this theorem. I mean, I feel like I haven't done anything except restate the definition of sigma. I can try to be a little classier by recognizing that at the very least, there's a formula for this kind of a thing that doesn't have an ellipsis in the middle. As I guess you guys remember from, I don't know, your calculus, pre-calculus classes, this is a geometric progression whose first term is a 1, and the first missing term would be p to the k plus 1, and the common ratio in each case is the p. Oh, I suppose since p is bigger than 1, most people would write it the other way. Yeah. So if you use this proposition, you can calculate values of sigma and tau very easily for prime powers. If you combine that with the theorem, which I haven't proved yet. Oh, do I need to write a proof? I guess that this is just the definition of sigma. This is now a formula from high school. I don't know. But just to see these theorems in action, if now I wanted to try to compute sigma of 12, then the right way to do that would be to say that 12 has got a prime power decomposition as 2 squared times 3 to the first. And so according to these formulas, I should be able to get the tau of 12 as, well, it's the product of, oh, sorry, I didn't finish what I was going to say. Sigma of 2 squared times sigma of 3. And this one in the same way will be tau of, oops, 2 squared times tau, tau of 3. The taus are easier to write down. I just have to add 1 to each of the exponents. So this part is a 3, this part is a 2. Let me put that exponent in there. So I get a total of 6. Did I have 6 divisors for 12? Yes, of course I did. And the sum of the divisors there should be, well, to actually use this formula, I would need to write this as 2 cubed minus 1, that's 7, divided by 2 minus 1, which is 1. And for sigma of 3 to the first power, so that'd be 3 squared minus 1, which is 8, divided by 3 minus 1, which is 2, so that's a sum of 4, and that gives me the 28 that I had earlier. Okay, you're probably not impressed that I could compute simple numbers in more than one way, but perhaps you'll be a little more impressed if I can actually prove this theorem. I will make it actually even more impressive by proving a more general theorem that puts these things into context. So let me make the following observation. The definition of sigma of a number n was I asked you to sum over all of the divisors of n. Just sum up the divisor itself. The same kind of a formula could apply for the function tau. The way you get tau is by counting the divisors, but a way to say that you're going to count them is I want you to range over the set of all the divisors of n, and every time you find one, and for each element in the set, you evaluate this expression, just 1. So you add up a 1 for each one of the divisors, and of course then what you will have will be the total number of divisors. You may recall that we actually had a similar thing for something similar that related to phi function. I had the Euler phi function on the other side of this formula before, but I did point out that if you take the sum of all of the divisors of a number n and evaluate the phi function, then you just get n itself. So you start to realize after a while that this is a pattern that people seem to use more than once. And it is a valuable thing to use. Shoot, I can't remember the terminology that people use for it, but you're taking the sum over all the divisors of n of one function applied to those divisors, and what you get on the other side is a different function applied to those divisors. And I mentioned this to you guys in a previous context when I was asked about, what point there is to the Möbius function. The Möbius function is actually related to these kinds of things. The terminology I gave you guys at that time is that you might want, if you had any function alpha defined on all positive integers, you might want to add up the values of alpha when d ranges over the divisors of n, and by so doing, you are evaluating or defining another function of n. And these two functions, alpha and beta, are related in more than one way. There's the thing called the Möbius inversion formula, which puts the alpha and beta on the opposite sides. I don't want to get into that right now. So this is a common kind of a setting to see. And here now is, I'm going to give you my theorem. If you have two functions, alpha and beta, that are in this relationship, and you know that alpha is a multiplicative function, then it's true also that beta is multiplicative. And let me share with you why I care about doing it in this more general context. By proving this general theorem, I'll actually prove both parts of this, where did it go? This theorem that I had mentioned earlier. I had a theorem that made me talk about two functions. I want to show that they're both multiplicative, but actually now I'm going to be showing that both of them are multiplicative, and many more functions are multiplicative as well. because both the sigma and the tau have been formed in exactly this way by using other functions that are calculated on these divisors of n. In other words, what I have here in both of these cases is I've got a function alpha of d. In the one case, alpha of d is just d, and in the other case, alpha of d is just 1. If I take the function alpha of d is just equal to d, would you say that that's a multiplicative function? Of course. Alpha, where is it to be? Here. If is alpha of m times n the same as alpha of m times alpha of n, if alpha of a number is just that same number, I guess you would say alpha is the identity function. And of course, that's true. If you just, in other words, if you erase all of the alpha, the phis, that's absolutely a true statement. I don't even need to use the fact that m and n are co-prime when I say that. For this particular function, where'd it go? For this particular function, if alpha of d is equal to d, then alpha of m times n is equal to alpha of m times alpha of n for any two integers m and n. Any two real numbers m and n for that matter. And in the same way, this is obviously a multiplicative function. I mean, if you evaluate that function at a product, are you going to get the product of the values of that function at m and n separately? Well, yes, duh, because all three of those numbers are just 1. So these two functions are very trivially multiplicative functions, and the sigma and the tau are computed from them by one of these summation tricks. So I'm going to prove this theorem for any multiplicative function alpha, and it will conclude that the corresponding function beta is multiplicative. And that will finish the theorem that I had listed earlier. By the way, let me point out that we proved at the beginning, or in the previous day, I reminded you of this theorem today at the beginning of the hour, that phi itself, the Euler phi function, is a multiplicative function. And when you add the values of this one together, you do get this function that I had described up here, alpha of n is equal to n, which is obviously multiplicative. So that's, I don't need the theorem to make that observation, but it does kind of just confirm that the theorem seems to be working, because you have a multiplicative function on that side and you ended up with a multiplicative function on that side. All right, so shall we prove this theorem then? Proving this will prove the things that I said about sigma and tau, and then I'll come back and talk about sigma and tau themselves. Okay, so let's have a proof. So what do you have to do? You have to convince me that the function beta is multiplicative, which means that I need to know that beta of m times n will always be beta of m times beta of n, assuming that m and n are co-prime. So assume that m and n are co-prime, and let's try to calculate beta of m times n. And I'm going to do some calculations. I'll rewrite this in a bunch of ways, and I'm hoping at the end of the day, I get beta of m times beta of n, and then I'll be able to put my little QED at the end. All right, so how am I going to compute beta of m times n? The only definition I have for beta is right up here. So apparently I'm supposed to take the sum of all of the divisors of m times n and evaluate alpha, this other function alpha, at each one of those. All right, well, what the heck am I supposed to do with this? I mean, I don't know anything about the function alpha. I don't know anything about the integers m and n. Seems hopeless. Except you do know how you get the divisors of an integer thanks to the fundamental theorem of arithmetic. If you took this number and you wrote it out as a product of prime powers, then all the divisors would be products of exactly those same primes raised to exponents that are less than or equal to the exponent that you've already used. So that's the same perspective that we were using in here. This is a simple case of a number that's been written in terms of its prime power decomposition, and all the divisors, I write them out explicitly. The same prime at the bottom, you just have exponents that don't go up quite as high. So, all right, I can just sit here and start thinking about all the possible divisors. Now, to do that, I will have to list out the prime factorization of m times n. Of course, that's easy enough to do. All you have to do is to take the prime power decomposition of m and n separately and just mush them together. You just add the exponents on each of the primes, the exponents that appear for m and n separately. I wouldn't actually get too far if I tried to do this in a general setting, but I do have this hypothesis that I haven't used yet. The fact that m and n are co-prime means that if you write m as a product of prime powers, just go over every single prime and raise it to some exponent with the understanding that most of those exponents are zeros. And likewise, n is going to be the product of those same primes raised to other powers. The fact that m and n are co-prime means that every single time you see a non-zero number for one of these exponents, then the other exponent is going to have to be zero. They can't both be non-zero. So in other words, if every time you multiply an e and an f together, you're going to get a zero. That's true for all I. So that's a fancy way of saying that m and n don't have any of the primes in common. That's what it means to be co-prime. Fair enough. So what does that mean in terms of getting the divisors of m times n? Well, to get the divisors of m times n, you're supposed to look at m times n and write down its prime power decomposition. Well, I've listed all the primes, and I've raised each, both m and n, I've raised those primes to different exponents. To get the prime power decomposition of their product, I would simply add those two exponents together. And then if you told me that d was a divisor of that, that would say that d itself was a product of exactly these same primes. Well, I'm imagining all the primes are listed here, but these would now be listed to some other exponent g, where g, each one of these g sub i's is less than or equal to the exponent that you see here, e sub I plus f sub I. Now here's the deal. I already just said down here that for each prime p, when you look at the exponents that show up, one of those two, at least, has to be a zero. In that case, when you're adding these two together, what you're really just saying is that g sub I is less than or equal to whatever the non-zero one was between those two possible values. So in other words, what you're saying is that for each I, let me write this out, for each I, either the e sub I is equal to 0, and then the g sub I needs to be less than or equal to the f sub I, or the other way around. Maybe it's the f sub I that's equal to 0, and then the g sub I needs to be less than or equal to the e sub I. Right, well, if that's the case, then here's what I propose. Take all of the primes for which you have a non-zero exponent showing up in here. Take all of those primes and split them into two camps. Take the ones where that positive exponent is less than or equal to the f sub I because the e sub i's are all 0. Put those onto one side, and all the ones where you had a positive g because the e sub I was the non-zero one and the f sub I was equal to 0. If you do that, then d turns out to be written as a product of two numbers, d1 and d2, where this is the product of all of those primes p sub I raised to exactly that power g sub I, but these are the cases where the i's are chosen for which the e's are 0. And then the other possibility is doing exactly the same calculation, but you only gather together those primes for which the f sub i's are equal to 0. So some primes show up over here and some primes show up over there. If that's the case, then you can say, well, wait a minute, this is a product of only some primes that have 0 exponents on the e's. That means that there's no reference to that prime in the prime factorization of m. And then you're only multiplying together primes that show up as in the prime factorizations of the other one, an n. And the exponent that shows up in the prime factorization of n, that's bigger than this exponent that I just shoved in there. all of that means that this number right here, this thing I call D1, that's actually going to be a divisor of n. And in the same way, the other divisor, the D2, that's a divisor of m. Because look, I'm only putting into this thing primes that show up with a zero divisor, a zero exponent in the prime factorization of that number n. So they have no factors in common with n, so they have to only be dividing m. But in fact, those primes show up with an exponent which is less than the exponent that shows up in the prime factorization of m. So this is a long-winded way of saying that thanks to the fundamental theorem for arithmetic, all the prime divisors that you get for the number m times n, the set of all of these d's, oh, I shouldn't use a vertical bar, well, anyway. That set of d's is actually the set of all products of a d1 times a d2, such that d1 is a divisor of n, and d2 is a divisor of m. That's exactly how you get all of the divisors of a product of two co-prime integers, is you take any divisor of the first and any divisor of the second and you multiply them together. It took me a long time to say that. I don't think it's actually all that deep of a result, but you do need to see that when you have co-prime numbers, that will give you all of the divisors. So in particular now, when I return to my formula for how b is being computed, I'm just going to rewrite this thing a little bit and say, okay, when you want to compute beta of m times n, that's going to be a sum over all of these d's. But the way you're going to make these d's is by taking d to be a d1 times a d2. I'll just put that parenthetically, where you're going to range d1 over all of the divisors of n, and separately, you're going to have d2 range over all the divisors of m. And for every one of those products, then, you're supposed to compute alpha of d. If d is d1 times d2, and you know that alpha is multiplicative, then alpha of d will be the same as alpha d1 times alpha of d2. I'm using, by the way, the fact that d1 and d2 are co-prime. When I said that alpha was multiplicative, that only means that I get a conclusion like this when d1 and d2 are co-prime, but that's forced by the fact that d1 and d2 are divisors of n and m, which are themselves co-prime. So there can't be any common divisors to d1 and d2 because there's none for m and n. Now, when you go to take this sum, this is a sum over a large, it's essentially a Cartesian product of the divisors of n crossed with the divisors of m. But as you take the sum over all of those pairs of d1s and d2s, you can split this into a sum. It's an iterated sum. You sum over all d's dividing n, and within that, you sum over all the d2s that divide m. And here you're supposed to take the product of alpha of d, I'll write it as alpha of d2 times alpha of d1. And I should put my parenthesis here, except I realize that as I'm doing this inner sum, the d2 is varying, but the d1 is staying constant. So I can actually factor out that alpha of d1. It's just the same repeated factor over and over again in every one of these products of two alphas. And now we're almost there. Here inside the parentheses, what you see is you've got the sum of, well, it's the sum of all of the values of alpha of d, where d ranges over the divisors of m. That's exactly how we defined this quantity, beta of m. And then you say, well, wait a minute, I'm going to take that number beta of m, multiply it by this number, add all of those products up. But in every one of those products, this factor stays constant. There's no reference to b1 in here, d1 in here. So I can factor out that constant. All I'm left with now is the sum over the divisors of n of alpha of d. And that's how we defined what beta of n is. And so I have, in fact, got what I put in there. I snuck it in a little corner there. Remember? I said that's exactly where I wanted to end up, is with beta of m times beta of n. And so I finished my proof. So just to state that again, the theorem was that when you take, so if you start with a multiplicative function and then sum over the divisors of an input, that'll give you another multiplicative function. And as a special case, that gives us the results about sigma and tau. Now I want to just come back. I know I have just 1 minute left, so let me return to this statement about sigma. The Greeks picked out the number 2n as being kind of an intermediate boundary that separates the deficient numbers with few divisors from the abundant numbers with lots of divisors. After they had identified that definition of what it meant for a number to be perfect, then of course the natural question is, well, what are the perfect numbers? And I already told you that n equals 6 is one of them. The next perfect number turns out to be 28. I invite you to go and actually calculate the sigma of 28 and see that you get 56. Next one after that is a little bit bigger. It's 496. You should notice a couple of things about these numbers. The first is that they're all even. So I have a homework problem for you. Is there an odd perfect number? And if you actually succeed in answering that question, I will give you a perfect score for the homework. In fact, I will give you an A for the class. Because, in fact, nobody has ever been able to answer that question. And in fact, that question is, as far as we can tell, the oldest unanswered mathematics question. 2,000 years ago, people asked the very natural question as to whether or not there is an odd perfect number, and nobody yet has found an answer. So, like I said, easy A, just have to answer one question. Okay, so let me stop here. There's some cool things that I can tell you about regarding the perfect numbers, not really questions exactly, but things that we could play with. I will put some of them in your next homework and discuss some of the others on Monday. How's that? All right, you guys got any questions for me to finish up the day? All right, so a reminder is we'll have a test next Friday. I will get it online as soon as I can figure out how I'm going to do that. You guys are going to send me any questions that you might have about, or any suggestions you might have about how to run the course or how to make the exams. And you're going to turn in some homework for me today. I guess the existing homework is due today. Oh, I do have, Andrew has a question, which is a good question. I will give you the answer so you're not in suspense all weekend. The question you asked, are there infinite perfect numbers? Please don't say that. What you mean to say is, are there infinitely many perfect numbers? There's no such thing as an infinite number, perfect or otherwise. But it's a good question. Are there infinitely many perfect numbers? And the answer is, we don't know. We do know this. Like I said, we don't know whether there's any odd ones. I can tell you what the even ones all have to look like. But the question then becomes, well, okay, you've given us a sort of a recipe, but does that recipe work infinitely often? And the answer is, we don't know yet. The answer is probably yes, but that's just a hunch. So, good question. All right, guys, I'm going to call it. I do have office hours at 3 if you have further questions. All right, I'll see you on Monday.
I have one question.
Oh, all right, go ahead.
Do these perfect numbers ever become useful in other subjects in mathematics?
No. Interestingly, this is a clear example of mathematics being pursued for its own sake. There is, as far as I know, there's really no good application of a perfect number.
Thank you.